All right. Hello, everybody.
Hello.
Hi, Abdul. Can you hear me?
Yes.
Dynamite. That's great. I had microphone issues last couple of days, so it's been a real adventure every time I got on a call.
Hahaha.
Hmm. Let's see where we are. We've got we're waiting for Lauren, I think. There's a Shook.
Hello.
All right. Let's see. Not yeah. We'll give it one more minute, then we'll get started. Right. I think we have 12 folks now, so let's declare quorum and go forward. All right. So I will.
It will exit out of the door that you entered.
Okay. I'll share my screen.
So once again, if you are on the right side,
All right.
like that at that door, and if you're on the left side of the aircraft, you will
Can
exit out
someone?
of the door that
There's
you
noise.
entered.
Can
Thank you.
someone mute, please? Thank you. All right. Can everybody see my screen?
Yes.
All right. All right. Very good. So let's get this out of the way. All right. So last time we talked about cabling and cable management. So first, I would like to ask for any thoughts or feedback from our discussion last week on cabling and cable management. All right. Okay, hearing none. What we had scheduled for today, I'll give an update on the storage solution for the OPGs. We'll talk a little bit about spine and aggregation networks. Ashok is here and he can share with us. He's my colleague from Broadcom, and he's been working with our architects on the connection maps for these systems. We can show where we are on that. And then I also can give a report on where we are with the draft document. I've been working on a draft that I'll be able to share tomorrow. And so I'll give a preview of that. So are there any other topics that folks would like to discuss today? Okay. Hey, Lauren, can you mute? Okay, thank you. All right. Okay, so hearing none. Okay, so we'll talk about, again, if you have other comments, please send them in email to Lauren and myself. Yeah, comments in writing are extremely valuable. Okay, so here is a revision of the basic OPG that we've been talking about. And I want to draw your eye, of course, to the right-hand side, that the storage rack has now been revised. And so we'll talk about what we've done and why we've done it. So I've now given it a special color, that orange color, to the elements in the storage rack. But everything else should look the same. The compute and networking racks have not changed. Okay, so we're going to talk about what is in, and Joshua, I don't know if he's on the call. I want to thank him in particular for giving me a lot of feedback on the storage solution. And so these what you see here reflect in large measure his input on this. Okay, so these are now the elements that are in the OPGM. And so, of course, we're starting with the V3 rack from OPC. And then you can see the various passive and active elements next to it. And of course, we've been talking about the NICs and the modules and the cabling. And what's coming up next, of course, we'll start the discussion today on the network topologies and the connectivity maps, how you connect these OPGMs to the spine and aggregation layer. And then next week, Lauren will start the discussion on the software and the management elements that go into these systems. All right. So this is the picture that has formed, at least for me, on how these storage systems are put together. So there are two elements, two principal elements in the storage system. There are the storage servers, and then there are the metadata servers. And so the storage servers are these compact 2U boxes, and this is quite common that storage systems are available from multiple suppliers, but everyone I've looked at that has a high performance system uses these 2U boxes, and these things are have a high number. They have 24 bays or slots that can hold NVMe drives, and they are capable of 4 by 400 gig data interfaces, and these are air cooled. Then there's another element called a metadata server, and this is in fact an x86 server. And what this really metadata, what they mean by this is the file system that at a very high level, the storage servers above hold the data, and then the metadata server knows where all the blocks of data are, because of course you have multiple storage servers. And the metadata server is also the one that interacts with and communicates with the CPUs and the XPU nodes whenever the XPU nodes needs to read or write from one of these storage servers. So in a sense, this is a file server. It's a file server function that has been optimized for these storage systems. And these are 1U boxes. And these also, what is pertinent here, you can have 2 by 400 gig interfaces on these servers. And so I think it's worth looking at what's at the actual storage devices themselves. And most typically, it's these flash drives, these high capacity, high speed flash drives. And so here's an example from one supplier. And this thing can hold 15 terabytes of data. And oh, there's a typo there. 15 terabytes of data. All right. And essentially this is, reading and writing are different speeds, but this is for planning purposes. This thing is capable of sourcing or syncing 100 gigabits of data per second. So the way these are used in these storage servers is they are grouped together, or they're clubbed together commonly, all right, into groups of 4. And so now that provides 400 gig. You can read or write to this collection of 4 of these NVMe devices. You can read or write 400 gigabits per second. So this can source or sync 400 gigabits per second. All right, so now let's look inside this RAID box. How is this thing organized? And so inside of each one of these things, you have 6. Remember, you have 24 of these. You have 24 bays. So you have 6 groups of 4 each. Any of these groups can source or sync 400 gig per second. Also, there are slots in these boxes for 4 400 gig NICs. So when you roll it all up, what's in this box? There are two high-speed CPUs. There are 24 drives that are grouped together to form 6 pools that can serve 400 gig each, and then you have 4 NICs. Okay, so there are very, very high performance drives out there. Now, this is not yet common for 4x4, or let's put it this way. I'm going to go ahead and, oops. There we are. So the storage boxes in this reference architecture look like this. So the rule of thumb for dimensioning these things is you need somewhere between 1 and 2 NVMe drives per XPU. So since we have 256 XPUs, if you divide 256 by 24, which is the capacity of these drives, you wind up with 10 and a half. You need 10 and a half boxes. So if you're using 1-for-1, so we'll have 10 of these servers in our storage rack. All right. And in our architecture, we'll assume that the servers have full bandwidth connectivity. But as we've drawn before, the XPU nodes will still have 2 by 100 gigabit storage links, one for each CPU. And so that will be our reference storage solution. Okay, so let me stop here. And any discussion on this topic is welcome. Joshua, are you here? Did you join? Not yet.
So I have a high level question. Are these storage subsystems providing any advanced storage features like deduplication or compression, or I mean, is that wrapped in? Okay.
Yeah. Again, you go to some supplier, and this is just this is the raw storage capacity, whatever it is. You go to whatever supplier, and then it's not RAID 0, it's just the raw storage rate. But they'll have RAID 2, RAID 10, RAID 6. Often it's proprietary. There's some little twist to it that puts the resiliency, the encryption, FEC, whatever features that the supplier is offering. But they all use the same machine on the bottom. The raw storage always looks like this. Did that answer your question?
Perfectly. Thank you very much.
Yeah. So yes, we're not handicapping which of them is the best. We're just observing that they're all built the same and that the interfaces are the same. That's all we're really doing here. Okay. So now that we have a better understanding of how this is put together, let's start seeing what it means to our OPG. All right. So remember, in our fully loaded 256 XPU system, we have 32 XPU servers. All right, now there are 2 CPUs. Each of them has a storage interface of 100 gig. So that means if we have 32 XPU servers, we have a total of 64 100 gig storage links that we need to connect to the storage rack. All right, so here's our solution. So you need a half-size switch, and this is in the networking rack in the middle of the OPG. And just to give it a name, I'm not perfectly happy with the names. If somebody has a better set of names, please let me know. But let's call this half-size the storage aggregation switch. And of course, its function is to aggregate these 6400 gig links. And then it connects to the leaf switch, which I'll call the storage leaf switch. This is the switch that sits in the storage rack. And if you just do the math, I need 8 by 800 gig to carry these 64 links. All right, so that goes here. And everything, since we're inside the OPG, everything goes over DAC. And now we need to connect this thing. This is not the only connection, of course, or set of connections coming into the leaf switch. We also have to connect the RAID boxes. So here are the data servers. And uh, I should mention that one of these servers is sufficient for managing the traffic, but the way this often is deployed, you have to have redundancy. So working in standby or, 1+1 redundancy here. So these are the connections. So if each of these is 4 and you have 10 of them, you need 40 links here for the data. And then if each of these has 2 400 gig links, you need 4 for the metadata data servers. Then if you roll it all up, and here's the, here comes the traffic from the CPUs themselves, you get 60 by 400 gig links. All right, that's the equivalent number. And so this goes to the spine. So all of this traffic from the OPG side is collected and goes up to the storage spine. And you'll notice the switch is not quite full. In fact, you could have an 11th box here if you wanted one for a standby. In other words, just a spare in case one of these boxes fails. There's room on the switch if you choose to do that. All right. And so now we know what's happening inside the OPG. Let's look now at what happens. And so now we're transitioning to the entire cluster. What does this look like in a cluster? Okay, so here we are. And we just talked about the innards in here. You have 64 CPUs, which have 64 100 gig connections. Okay, this aggregation switch collects those, passes them over to the leaf switch here. And then you'll notice that to make a 1K cluster, which is the example that we're going to work, I'll need 4 of these OPG 56s. So you take the uplinks from the 4 leaf switches and you distribute them across the storage spine. And so if you just do the math, that means that you need 15 connections because there are 60 per leaf. You send 15 by 400 gig to each of the spine boxes. And what this accomplishes, let's go back here. Let's go back to this. Inside the OPG, obviously, given that all of this is non-blocking, any of the CPUs can read or write to any of the storage servers. That this provides perfect non-blocking full access between this side and this side. But by having the spine layer, not only can any CPU inside of OPG number 1 access any storage server inside the same OPG, because of this spine that's present now, any CPU anywhere in the cluster, there are 1,000 of them, or there are 1,000 XPUs, so there are 256 CPUs. Any CPU anywhere in the cluster can access the storage pool anywhere. That's what this architecture accomplishes. So this is the fundamental upgrade to what we had before. It wasn't simple aggregation. This is what Joshua explained to me, that in fact there's a storage spine that any CPU has non-blocking access to any storage pool anywhere inside the cluster. All right, so let's stop here. Any discussion or questions on these 2 slides? All right. Okay. So that is the storage piece. All right, and I will upload these slides today. Okay, so now, Ashok, are you online?
Yes, I am.
Lowell.
Good. Okay, are you ready to share what our thoughts are so far on the connection maps?
Yeah, so just
Okay.
to be very clear, this is still work in progress. I don't have them yet in the OCP formatted slides, but I'll share what I have as a basis for discussion more than anything else. 1 second, let me share my screen. While I do that, let me introduce myself. My name is Ashok Raman. I'm also a product manager in Broadcom switching group, and I work with Lowell quite closely. Can you see my screen?
Yes, we can.
All right, 1 second here. Okay, so my primary goal and role here is to help Lowell with some of these connection diagrams and to help help him flesh out completely his proposal for the OPG solution. Let me enter. Okay, so this is again just a representation of the OPG 256 that is going to serve as the basis for all our contributions. And what we started looking at is, okay, how exactly do we connect from the XPUs on the left to the networking racks in the middle? Okay, so I have blown that out. Just one example of how we would do this. If we build the OPG 256 cluster from inside out, that means we would start with the two
Oh,
inner.
and Ashok, you should mention that we're starting with the Clo network.
Yes, sorry. This whole thing is premised on the Clo network, and we will have in the future a solution for the rail optimized network as well. So in the Clo network, if we started to build small and then expand out till we fill the 256 XPU solution, we would sort of maybe start with just 64 GPUs, and these are numbered here as a N1 through N8. And we would have the scale out switches, which are labeled SOS 1 through 4 in the middle in the networking rack. But in the beginning, we would populate only one switch, SOS 1, and we would have connections from the N1 through N8 to the SOS 1 switch. So that switch, and I'll go into more details on that switch in the next slide. So this is just a representative example of how the connections would look. The red arrows show the connection, red lines really show the connections between the XPUs and the switch ports. These would be sort of the downlink ports in common terminology. And the blue lines indicate the connections between the SOS1 switch to the spine switch, which is the set of switches, the set of boxes on the top over here, if you can see my cursor arrow. Okay.
And Ashok, if you let me interject, we're doing this, we adopted this inside out strategy in response to feedback from earlier discussions that we should strive for designs that enable low impact growth. And so that's the motivation. So we could have started left to right or right to left, but the point was to enable, as Ashok just described, easy growth of these systems.
Okay, so I'm moving on to the next slide. And I'm going to spend this slide to talk about the connections in a little bit more detail. The scale out switch, at least for the purposes of this discussion, we're assuming it's a 51.2 terabit per second switch with 64 OSFP ports, and assuming the ports are numbered from 1 through 64, as opposed to 0 through 63. It's a minor but not inconsequential numbering thing that we need to keep in mind. And the switch is configured in 128 by 400 gig mode. So it has 128 400 gig ports, but there are 64 sort of faceplate ports. So our presumption is that, or rather our assumption in this analysis, in this description, is that we will connect the odd numbered ports 1 through 5 on the switch are connected to the XPU ports at 400 gig speed. That means essentially we need a 2 by 400 gig DAC splitter cable on each end between the switch port and two 400 gig XPU ports.
Okay, Ashok,
Yeah.
I think actually, yeah, the small correction to your drawing on the right-hand side, the switch, there's just a single connector there. That's an 800 gig connector at the OSFP.
Okay. All right. So my bad. Okay, I'll correct that. Yes.
Yeah. So yeah, there's a single. I mean, that's why we have to do this. That's the motivation for this is we only have 64 ports to work with,
That's
but we
right.
need 128 legs. Go ahead.
And then even numbered ports on the switch are connected to spine ports using fiber with maybe, again, I need to correct this with 400 gig splitters on, I don't know if you need 400 gig splitters on each end. but I need to think that through a little bit, depending on
Yeah.
whether the connection to the spine switch is, again, it's an 800 gig OSFP port, but we can probably just populate a single cable. Let me make that correction here.
Yeah, no, the way that works, the way the optics work is the OSFP modules have 2 ports. So in fact, it's 2
Yeah.
optical cables.
Okay, all right. And this is how then the connection is
Right.
gonna look like. Right.
That's
And
right.
yeah. So on the left, you have the XPUs. On the bottom, really, you have the XPUs. And you have the switch here, and the red connections show the connections between the NICs and the switch. I will, of course, correct for the splitter.
Mhm.
That is the odd numbered ports, and the even numbered ports are all going up to the 400 gig uplinks. And this is going to be repeated for the entire cluster.
Yeah.
So this is as far as I've gotten so far, and I'll work with Lowell to correct these diagrams. But this is the idea, essential idea, I hope is clear, that we would have the odd numbered ports connected to the XPUs and the even numbered ports going up to the uplinks. So it's 128 by 400 gig. That is in this generation for 400 gig connectivity. And of course, in the future, as we build out 800 gig connectivity, essentially this will remain very similar, but the specifics will of course change.
Okay. Any
questions on
discussion?
this?
Any discussion on this, folks?
I just have a quick question.
Sure.
So this looks like the leaf switch. So is it leaving this switch on the uplinks? Is it
Yes.
leaving this and connecting in the cabinet to the spine, or is it going outside?
No, the spine is outside. So that
Yeah.
that the assumption here is that the local cabling is copper, it's all inside,
Mhm.
and then everything you see, look at the networking rack.
So those are patch panels at the top?
You got it. That's fiber. Those are fiber patch panels. That's right.
Okay, thank you.
Yeah. And so James, I saw your
But-
comments.
but-
Go
If
ahead.
it is fiber patch panels, the OSFP module does have dual 400 gig MTP connections. I heard you say one, but if we're talking about fiber.
Yes. No, it has dual. It absolutely has dual. Yes.
Okay.
Yeah, I'll show that in a second.
Okay.
Okay.
The other
And
thing-
James,
sorry.
go ahead. Go ahead, Ashok.
No, I think that's all in terms of the slides. I was going to show the connection map.
Oh, yeah, please. Yeah, please do.
Yeah.
Please do.
All right, give me a second. Yeah, 1 second. This is going to be a bit. Yeah, so it's a bit, I'm just showing this at high level. So we built a 64 by 64. Let me zoom in a bit.
Yeah, just zoom in and show the upper left-hand corner. There you
Yeah,
go.
yeah.
Beautiful, beautiful.
Right. So what we are doing is, this will be sort of as a check for people to make sure that the connections are correct. So you can build an XL that basically ensures there's only one connection between a NIC and a switch. So for each XPU, it has 8 NIC ports, for example. And then we are just showing how NIC 1 will connect to port 1A on the switch. NIC 2 will connect to port 1B on the switch. Then port 2, A and B, which are basically the uplink ports, are blank. There are no NIC connections. And so we're basically showing that the odd numbered ports will have connections to the NICs, and the even numbered ports will have connections, will have no connections in this connection map. They're all going up. And to ensure that, there's some very simple rudimentary checks we've also implemented in Excel, confirming that each row has only one entry. For example, let me see. Yeah. So this is a simple checksum kind of thing. That each row has only one, each pair of rows has only one entry, then the all the next set of rows will have entries of 0, and so on and so forth. They're very simple checks. So we can really expand this. This is really just to illustrate how we can build these things in Excel to allow for some simple error checks, so to speak. And at the bottom also, we'll have, again, checks to confirm that there is only one entry in each row.
Each column, yeah.
Each column, I'm sorry, yeah.
Yeah.
So it's pretty simple stuff.
Okay, so, and I think what this illustrates, and just to emphasize, if you could go right back up to the top left-hand corner, there you go.
Yeah.
That it's our intention to publish an explicit mapping. And so we're going to describe which port on each which XPU is connected to which switch port. That's the point here. And the reason we have A and B, of course, is that we're splitting the 800 gig, we're breaking out the 800 gig OSFP ports into two 400 gigs. So that's what that means. It's, it's OSFP port number 1, and then it's 400 gig ports A and B. That's what that means. And also, James, I saw your comments that you would, instead of inside out, you suggested middle of row, and you also suggested the term breakout cables instead of splitter cables. Those are good improvements. We'll adopt that terminology. That sounds good. Okay.
All right,
So-
that's good. Yes, I'll do that.
okay.
Okay,
Any-
that's all I have for today.
Yeah, that's fine. Any comments before we shook? Any comments on the connection map, the direction the connection map is taking, or the format?
I have maybe a dumb question.
Sure.
Why did you choose the mapping where it's a downlink, uplink, downlink, uplink?
Oh, okay. I mean, in principle, they're all equivalent. It's just important to pick something, right? Just
It
pick one and
shows
document it.
one-to-one,
Yes.
basically.
Yeah, and so, our thought was that it's really, how can I say it? It's as you're going across as you're plugging stuff in, just alternate, just to make it harder to screw up. Up, down, down, up, down, up, down, up, down, up. You're plugging it in like that. That's the idea.
Okay, got it.
I mean, it's not a strong reason, but it's just pick a method and stick with it. That was our idea. So,
Thank you.
okay. So now I'm going to the last thing I had, if I may share. All right, I want to share the draft that I have. Okay, can you folks see this?
Yes.
Okay, so what I've done is I've collected all the material that we've discussed over the last few weeks, and I put a Word document together, and I'm pretty much caught up with everything that we've discussed so far, and I'll show you that. And there of course is the standard material at the front, the license, compatibility with the OCP tenants. And what I've done is just take the material that we put in the white paper and put it in here. So it should look very familiar. So this drawing and this text is in the white paper. You'll see it here as well. All right, this is, just defining terms. What do we mean by a pod or an XPU node? And what do we mean by a cluster? And then down here, we talk about the different networks. And then here's where we start to define the terms that we've been using. Of course, we've been describing these things called OPGMs. These are the open pod groups. And then you have to have a spine or an aggregation layer to knit all this together into a cluster. All right, so now we start on the definition of the OPG. And so here's the revised drawing that illustrates this, the cartoon that I hope illustrates what we're talking about. So you'll see we have the updated drawing of the storage rack on the right-hand side. Then I've also made this table just to try to collect all in one place the elements that will be described in this document. Of course, here are all the physical pieces, the cabling, the NICs. Here's the optical modules, and I'll show you what that looks like in a second. And then, of course, Ashok just shared with us the direction on how we'll describe the network topology and the connection maps. And we'll do rail optimized and CLO. That's our intention for these bigger systems. And then Lauren next week will start the discussion on the software elements. All right, let's keep going. There was also some suggestions a couple of times during our earlier discussions that we write down our assumptions. So I've made an attempt to put down what I think are the assumptions in putting these systems together. And so I've got 15 of them. I'm sure there are more. We're inviting all discussion on this in particular. Okay, now the physical elements. Here, again, this is fairly straightforward. We've agreed from the beginning to use the ORV3 racks. And so I tried to put all the passive stuff in one place. So you'll see fiber management panels here, cable management raceways, and then there will be a power unit down here. So this is just the basic infrastructure of these racks. All right, then just some of this is pretty simple, that if we want to enjoy the benefits of DACs, then we have to provide cable management hardware for it. We need to put in these horizontal raceways, optical management shelves. Of course, we'll have local fiber jumpers within the OPG. Then there will have to be fiber management shelves where you cross connect the jumpers with the plenum or the trunk cables. So those go there. Power supplies. Okay, then the XPU nodes and NICs. All right. And again, I've just tried to pretty up the pictures. We discussed this in our meetings. Here is our model of the XPU node. And so, of course, there are 10 NICs, 8 of which serve the XPUs, 2 of which serve the CPUs. All right, and then I just wrote in English all of the assumptions we discussed about what's going on inside these nodes. All right, the storage system, we just talked about this. So again, there are the two essential elements of the storage system, the server and the metadata server. All right. So I captured the fundamental requirements for those. We had a separate meeting, as you recall, on the switches. So here are all of the switches that are needed to put these things together. So these, they're scale out front end and storage switches, come in 2 sizes, the 51 and the 26 terabit sizes. And then we'll need, depending on where this shows up in the system, a 24 port management switch and a 48 port management switch. All right. And so I'd really appreciate it if people would read through this and find the bugs. Okay, here are, I think this addresses your question. We're assuming 800 gig OSFP modules, and there are 2 ports. So each of these gets 2 separate fiber jumpers. So there are 2 separate cables coming out of these on the optical side. And then, of course, we've talked about the DACs for the local high-speed connections, and then the management connections. I think this is obvious. Cat 6A is a good choice for the management connections.
Hey, Lowell,
Sure.
a quick question. I assume those 800 gigs are for that the back end scale out network. Is there a front end? Is there a picture for front end / storage optic in there that might be the 100 gig version that we because I see the
Sure,
800, which is the 2 by 8 duplex MPO, but I didn't see anything for 100 gig.
Okay, let's go back over here. Hang on. Where are we? This one. The assumption that we've been operating under is that all of these connections inside the pod are DAC.
Got it. Got it. Okay.
So yeah, okay. So all of these connections from here to here are DAC. Then you can, from here to here, you can make this jump with an 800 gig DAC. But leaving here, it has to be optical. So you'll notice, let me blow that up just a little bit. You know, half of the ports serve the servers and this switch, half of them leave the OPG. And so here are fiber management panels. So you can have jumpers from here to here. And these are 400 gig jumpers.
So I guess a better way to clarify what you showed in the 2x400 2x400 optic is the blue. Is there an example of what would
Oh,
be
it's the
a
same one.
red? Same one. Okay, same one. Okay.
Same one. Same. Yeah, we're
Okay.
trying to standardize on 400 gig everywhere, And the exception, of course, are the lower speed 100 gig. And then there are I think 8 cables that are just 800 gig to 800 gig, just running across here. So that's the only exception I can think of.
Okay.
Everything else in the system is 400 gig.
The same. Okay.
Yeah, that's in terms of inventory and all of that, it's the right thing to do. Okay,
That's exactly
so
where I was getting at. Yep. Thank you.
sure. Okay, so then let's go down here. Let me see, where were we? I think we're almost done here. Okay, so we talked about the shelves. Okay, so again, I'm just trying to pretty up the pictures. We talked about what goes into these XPU nodes, and I've tried to capture all of the assumptions we discussed. The storage subsystem we just discussed. All right. All right, the switches, again, they're only color-coded to show which network they're in. They're all the same switches. They take the same DAC cables, the same optics. That's the intention here. I just color code them to show which network they're in. But this is meant to be, they're meant to all be the same, functionally.
Do you think people will have questions about why we're using such a high-powered switch for the front-end network? I mean, I understand you're aggregating a lot of 100 gig in there. You should maybe just say something about sparing or
Okay,
some
you're talking about
justification.
this thing right here, this half size. Okay, or this one? Okay, the reason that I haven't used this one yet, this one goes up in the spine, up in the aggregation layer. On the, I'll describe that. That's a good catch. Down here, let me pull up my picture again. You only need the half size to pick up all the front end traffic. You'll need the half size to pick up the storage traffic. But once you get up into the spine or aggregation layer, you need the full size when you're collecting traffic from multiple OPGs.
Yep, I see.
Okay. But the idea is that it's one generation of switch. Probably people putting these systems together would like to choose one switching supplier and buy all their switches from that supplier. So it's the same software, same management, but they use them in 3 different networks. So that's the basic idea. We want to enable that, facilitate that. So that's one reason to try to use the same same optics and all of that. Okay, so let's go on down. Okay, we talked about the cabling and the optical modules. So I captured that here, and I just tried to summarize what we've talked about. So again, it's an optical modules are 800 gig OSFP, and there are 2 connectors on it, on the back end of that. And then we're recommending the use of single mode fiber cable and single mode optics. There's every reason to use the good stuff to minimize problems with these links. All right. And again, we're recommending the heavy, stiff stuff so that you can get extended reach performance out of these DAC cables. And again, just standard Cat 6A for the out-of-band management ports. Okay, so the new thing that I haven't shown yet, I'd like to share it here. We were asked when we kicked off this effort to also make infrastructure, to give guidance on the infrastructure requirements for these things. And so I decided the best thing to do would be to build tables. And so these are straw man tables. And I would really appreciate review and comments on these. So I built 3 tables. We'll come back and look at them in a second. I built a compute rack table, a storage rack table, and a networking rack table. And so if you look inside of them, these tables estimate 3 things. They estimate for each rack how much of the rack you use. So that's fairly straightforward. You know, the 44U racks, we're using 38 of the 44 of the vertical positions. We're using 38 out of 44. So this rack is pretty full. This is mostly full, this rack. And this also estimates the power consumption and the weight of the rack. And I just went off, you know, I just did a survey of representative products in this space. And so you'll notice that here are the XPU nodes. We actually talked about the power when we discussed those. And then I got, you know, estimated weight of the cable management and the, you know, the power distribution and so on. So we have 3 infrastructure numbers for the compute rack. And then I also made estimates for the storage rack. And so again, it's the storage rack is mostly full. We use 38 out of 44 OU, but you know, it pulls less power, but it's still pretty heavy. It's 500 kilograms. So these are 1-ton racks. And finally, the networking rack, same estimate, you know, again, it doesn't pull very much power. The rack's about half full, and it's considerably lighter than the other 2 racks. So this is the proposal for how we address the infrastructure requirements for these systems. So let's stop here, and discussion is welcome.
So, Lowell, this is for scale out or scale up or both?
Oh, this is for scale out, scale up, storage, everything.
Everything.
Yeah, if you,
So-
I'm just counting how many switches are in here.
So, how we define a scale up? If I have a rack of
Oh, no. The scale up in these systems is inside of each of the XPU nodes. So the weight, power, and all of that are already comprehended when you get the weight and power of the XPU. It's inside of each of those boxes.
Exactly, because some people they think a scale up also includes a case when you add more servers. Sorry, scale out is when you add more server to the rack.
Well, yeah. Well, this is full. This is completely full. There isn't any room for any more servers.
Okay, but if we add more servers to a rack, is that scale out or
Well,
scale?
no. Yeah, all right. If they are these if you could do it, if these servers somehow magically got smaller, so you put more of them in the rack,
Yes.
then every time you add a server, you're adding scale up inside the server for this generation of equipment.
Scale up. Consider this as a scale up. You're right. Okay.
Okay.
Okay. So your definition of a scale up is adding more capacity to the rack.
Yeah, again, this 400 gig air-cooled generation of equipment. The scale up is inside each one of the XPUs. And so it's a black box. We don't really say much about it.
Exactly. I agree with that definition. Yes, you're right. My last question.
Sure.
The wiki says this is version 0.3, but when you open the file, it is version 0.1.
Oh, well, that's an editor's error.
Okay.
Okay. I'll take a look at the draft.
Yeah.
Okay. Draft
And
version.
the draft you reviewed with us will be added to the wiki, right? The one you showed us now.
Yes. I will put it up tomorrow. I
Yeah.
have one more review meeting, and then I'll put it up tomorrow.
Yeah,
Okay.
because it is much more detailed.
Yeah, well, the first one was just the white paper, which had no details on purpose. But
Yeah.
this is meant to be the reference architecture document, the first of them. So again, This is just what happens inside the OPG. My next job is to put together a document which should be much simpler, which just basically describes the spine and aggregation layers. You know, the topology and the switches and other facilities needed to put these things together into a cluster.
Thank you.
Yeah, sure. Okay, other comments on the infrastructure tables here. Okay, so now I'm going to show you the parts that are empty, and I've left room. And so, Lauren, I think you're up next week. As we have discussions and go through the software and management, then we will start to flesh out this section. We'll put in descriptions of the recommended software and management solutions that go with these. And then Ashok has showed you for the topological elements. Okay, we're going to put in here the connectivity maps for CLO and for rail optimized systems. All right, and so that's basically, and as we described, we're going to have 3 versions. This is the one that is useful for building big systems like 1K XPUs, 4K XPUs. This is for systems, and it's just really a cut down. This will be for systems with between 129 and 256 XPUs. And then this will be the smallest system. So this is how we will be able to cover all different sizes, from small to large clusters. And so these should be a very small amount of work, B and C, since they are just cut downs of the one we've been talking about. Okay. Any other comments or feedback on this? All right. So I'll share the Word document, Hesham. I'll upload that tomorrow. I have one more meeting on this to review some things I don't quite understand. And then I'll upload it, and I would like to invite everybody to download it, read it, and please capture your feedback, and we want to improve it. Okay. Anything else, folks? All right. Well, hearing none, thanks a lot, and everybody have a good long weekend.
You too. Thank you.
All right.
Thank you
Thanks,
very
folks.
much.
Thanks.
Bye.
Bye-bye.
Bye-bye.